My dear students of CE703, Design of Concrete Structures 1, I am Professor F.M. Abdurrauf speaking. Today we will discuss another new topic, and that is development length. In concrete RCC, we have two materials. One is steel reinforcement, another is concrete. These are two different nature of material, and they together combiningly they perform some activities, and these two materials are quite different. But as we have discussed in earlier class, that these two materials have some properties. Those are very significant for be used in combination, so that the concrete will take the compressive strength and steel will take the tensile strength or compressive strength wherever is necessary. In this topic, we will be discussing how these two material combined together remains intact and the bond is developed, so that one does not easily is separated from the other one, and some forces can be applied both in concrete and both in steel. Now we will mainly deal here with steel embedded in concrete. Steel is normally embedded in the concrete, and steel sometimes will require to give tensile strength and sometimes compressive strength. And if we embed a steel bar in a concrete block, we can pull it out if we embed this a small amount of the steel bar into the concrete. But if we embed a sufficient length of steel into concrete block, then we cannot pull it out. And if we apply bigger force, then the bar will tear off. Instead of coming out, it will tear off. That means the bond capacity is more than the actual tensile or compressive force capacity of the bar. Now we will be in this class, we will be dealing with the length of this bar, or what length of a bar should be used in a concrete, so that the bar does not come out of the concrete, but it resists strength, stress, it resists strength, some force, it resists some forces. So here this is a little bit complicated item, and I have tried to make it simplified so far as possible, and even that you have to go through it very rigorously and repeat it for understanding the material, and then you will be able to understand the thing. Just by once giving a glance to the text, you will not be understanding. And mainly we will be dealing with some formulas, and we will try to understand the parts of these formulas, elements of this formula, and gradually we will be able to come to a conclusion of this problem. That means how much hot length of a steel bar should be embedded in a concrete block or concrete structure or concrete member, so that it will not, if it is in tension, it will not pull out, and if it is compression, it will not crush in. And here mainly we will be depending on a formula given by ACI code, and a single formula where they have included many items. And if you see the formula first, it will be very cumbersome, but we will be dealing this formula part by part. That's why whenever we do these parts, then if we can understand that part, that part will be easy, and then we go to the next part. and then we will go to the next part. This formula is a big one, and there are several parts and several items is there in there, several factors are there. All these factors is to be understood, and you should be able to find out the values of individual factors. But ultimately the formula is a big one, but the factors are factors, and the individual factors are to be understood, and then it is to be applied in this equation. And finally we will get this, the length of the bar, what will make the structure sound, and the bar will not come out or not crash in, but the balance will be there. Either the concrete, normally we in the design of concrete structure, naturally we like that the steel should fail in any case, because the steel fails gradually and concrete fails suddenly. Here also we will be seeing that the steel comes out and elongate. If it elongates, then it will show that the steel is failing. Then we can take some precaution of the structures. Now we will go to the formula directly to the next page. This equation is a big one. Equation number 8.1 is a big equation. So far the RCC design is concerned, this is the most cumbersome and complicated equation you will face, though, and we will try to divide this equation in parts, and every part is separate one, and we will discuss every bit of these terms separately, and then you will be able to understand the whole thing. And in the long run, some of the factors are to be memorized for the use in examination hall or problem solving, and some of the factors are to be decided about what factor you will be using, like Fy, F prime C, or lambda. Here you can see several factors. We are familiar with Fy and F prime C only here in this equation, and dB is the diameter of the bar. At the right hand side, outside this bracket, the dB is the diameter of the bar, and in this diameter of the bar we will getting from the design of the beam for tension and compression, bending moment. From bending moment we will be knowing the diameter of the bar, what diameter of the bar, how many number of bars will be there. Those we will getting from the moment design. And here, if we start this equation from the beginning, 3/4 is a numerical factor. Fi is, that Fi is the yield strength of the steel, and that is whether you use 40 grade or 60 grade steel, it will depend on that, the development length. And in the below Fi there is a lambda factor, and lambda factor is aggregate factor. There are in the nature in our country there are in major two types of aggregates are there available. One is the stone aggregate, another is the brick aggregate. That's why depending on the aggregate aggregate type, this lambda factor will be coming. Though the value of this lambda factor is given below. For stone aggregate concrete, the lambda factor is 1, and for brick aggregate concrete, the lambda factor is 0.85. This lambda factor of 0.85, you have to remember it, because this lambda factor will be required in as you have seen in shear design also. And wherever the lambda factor comes, the value of brick aggregate factor and the stone aggregate factor must be put there. Stone aggregate factor has a lambda value of 1 and steel and brick aggregate of 8.5. And A prime C is the A prime C with which you have designed the beam, whether it is 3000 psi or 4000 psi concrete. That's all. Now the Fy is yield strength. In this equation, at the top there are three factors which are denoted by psi. This is a new alphabet, Greek alphabet, and its sound is psi. Normally we are not very much associated with this symbol, but we have to learn this symbol psi for the sake of development length calculation. Psi t is the symbol for a rod where it is used. The rod is used at the top side of the beam. If steel is placed at the top of a beam, then we will be using psi t factor. T means top, and psi e is the next factor. E is epoxy. This is a new term, epoxy paint. Sometimes to protect the bars from weather action and rusting, some paint is given. That paint is known as epoxy paint, and the factor for that epoxy paint is psi e. And psi s is the size factor. Our rods we will be using different types of rods, different size of rod, 5/8 inch, 7/8 inch, 1 inch, 1.15 inch, etc. Depending on the factor, depending on the size of the bars, there will be a factor, that is psi s. We will be specifying these factors in numerical value later on. And on the right hand side, the diameter of the bar will be placed, because diameter of the bar will be decided earlier in the moment design. Now the bottom, there is the lambda and root over A prime C. You know A prime C is concrete strength, and within the small bracket, first bracket, CB and plus KTR. These are the two new factors. These are the two new elements. Those will be coming up here, and we will discuss that in detail, and we will show calculation also. CB is the spacing or cover dimension. Spacing means spacing of the bar from one bar to another bar, and the clear cover spacing and cover dimension. At the side bars there will be cover dimension, because after these side bars there will be 1.5 inch clear cover, and the clear cover and spacing of the bar, the distance, what concrete is there in between two bars, that is to be calculated, and that is CB. CB is the spacing or cover dimension. Spacing means rod to rod spacing divided by 2 is the CB value. We will speak this about in more detail, or in the numerical problem. These will be more clear, and we have to know this. CB is the spacing or clear cover dimension, side cover dimension, top cover dimension, etc., etc. And KTR is another term. It is dependent on a stirrup design, stirrup placing, stirrup spacing, stirrup size, etc. And here also there is dB is the diameter of the bar, because diameter of the bar is known to us, because we have decided it about this diameter of the bar in moment design. Now we'll go. These are the factors. All will be coming up in one equation, and we will gradually put one by one numerical values of all these factors. Then we will come out with a LD development length in inch. have pointed out some of the points earlier. That's ATR, total cross-sectional area of all transverse reinforcement. That means in the transverse reinforcement, ATR, area of transverse reinforcement. That is the normally we usually in a beam there are two legs of stirrup, and the area ATR is the diameter area of stirrup multiplied by 2. S is the spacing in inches, and S maximum spacing of transverse reinforcement. Stirrup spacing is the S value, where the spacing is maximum at the near the middle of the beam, or where the shear is less, there is spacing is more, and that spacing will be taken up in this case as S. The number of bars is number of bar and wires, etc. And n number of bars being developed. If there are 2 bars, then there will be 2, and if there are 3 bars, that will be 3, and there are 4 bars, that will be 4, etc., etc. And if for simplification sometimes, and we can use this KTR, which is a little tough to calculate. Sometimes it is KTR may be used as 0 for approximate solution. And the limit of 2.5 on C plus CB plus KTR by divided by 2 is imposed to avoid pull-out fail. There should be at least the limit of CB plus KTR divided by 2 is a term in the equation, is a part of the equation. There we should not use the limit of 2.5. That means we cannot use values less than 2.5 there. And here is another requirement in this page, in the middle paragraph, that the concrete strength in root over F prime C should never be taken as more than 100 in this equation. This is one of the requirement, that is root over F prime C should not, of course, to root over F prime C is equal to 100 is very high strength concrete, and we should, if the concrete strength is more than that, then we should not use this value of root over F prime C more than 100 in this equation. And this is the complicated or more rigorous equation, and there are some simplified equation, and because this is a very complicated equations, the ACI code permits some simplified equation also. For maybe a little rough calculation is there, but that is also sometimes is allowed, and the development length in that in simplified equation will give some little more value than the rigorous calculation. But for to avoid this complicated formula, this is also allowed, that we can use this simplified formula also. If we want to use simplified formula, we should follow some requirements, that the beam should be designed in a proper way and a standard way, and spacing of the stirrups, etc., should be followed by ACI code properly. And then though the length of this development length here, we will get a simplified equation, the length will be little more, and that will not be too much for uneconomy, because we can use this as simplified equation also if we want that the more rigorous calculation should be avoided. But where the case is a critical one, where the rods placed in proper way, the stirrups are placed proper way, and all specifications are followed properly, then we can use this simplified formula also. And if we want to make it uh, economic, then we have to go for the rigorous calculation. In the main equation, the development length sometimes is less. In most of the cases, the main equation give you the development length less smaller than the approximate formulas, simplified formulas. So depending on the situation, how many times this calculation will be repeated in a building. If it is many times, then we have to go through the rigorous formula, complicated formula F, and if we design one or two beams, then we can go with the simplified formula. Equation 8.21 and 8.2b, 8.2a and 8.2 are the simplified equations. And here the division of these two is the division of these two equation is the size of the rod only, and the number 7 bar and number 6, 7 and above and 6 and below. The first one is for the bars 7 and larger than 7 and larger bar, and the lower equation is for number 6 and smaller bar. These two equations are same, but only the coefficient, the numerical value of 20 and 25 is used. 20 is in the top formula 8.21a, and 25 is 8.2b. If the diameter is smaller, the surface area is more in comparison with the area. That's why the factor here is 25, and the top equation requires 20 as factor, and the bottom one is 25. Is because the smaller the size, the surface areas in comparison surface area is more. That's why the development length will be less. And these two equations are frequently used, and normally we will use this one where we do not want this rigorous calculation and the length difference for the simplified formula and the rigorous formula or integrated formula and the complicated formula. There is a significant amount of difference there also. It's not very close, but if, as I have said, that if we are going to repeat this one calculation for many beams, then we must go with the rigorous calculation or more complicated formula. And if we are not repeating it many times, then we can go with the simpler formulas. And in some of these cases, in slab, etc., there will be no shear. As in slab and other things, as there is no shear reinforcement and the slab spacings spacings are more, than in that case we can use the simplified formula. Next. Now we will discuss anchorage by bends and hooks. The normal bend or hook is given in figure 8.1, and you can see this drawing in the next page. That is, there are the main bar and stirrups will be coming up. The main bar is a big bar, big size bars, and stirrups are small size bars. In main bar there are two types of hook or bend. One is 90-degree bend and one other is 180-degree bend. You can see that in figure 8.1, and the top two figures are there. Though these figures are a little smaller in size, but in reality the whatever is the size that will be coming with the rod size, etc. And all the details of this hook to be bent, how much radius should be given, how much extension of the straight bar will be required, all these are listed here. This cannot be memorized, or there is nothing to be understood. You have to follow these things by seeing charts and figures whenever you design a beam or whenever you make a final drawing of the bars, etc. You have to keep these figures in front of you and try to follow some of anyone which is suitable to your design, etc. That's why we will not be detailing this with dimensions, etc. There are two things. One is a bend diameter, that is D, and the numerical values are listed in this text, and there is in some extension of a straight portion, and that the dimension or the distance or length of this also is given in this table depending on the size of the bar. And as this depends on the different sizes or group of size, that's why one cannot memorize it, and there is no need of memorizing all these things, but you have to know that there is a list, there is figures, and there is values listed in table or in a text, and from there you have to take these values depending on, say you are using 5/8 inch bar, and we have to go, this 5/8 inch bar is from here we have to find out the diameter or the extension for 5/8 inch bar from this list of values given in this text. Again, in table 8.1, we have listed bar size and minimum diameter. This is simple, and whenever you use a number 9 bar, you have to use this 8 bar diameters for making this bend. And if you use number 3 to number 8 bars, you have to take the diameter of the bend as 6 bar diameters, and that's all. My dear students, now we'll discuss one example of development length. Here in the figure, left hand side, we have shown a beam and column joint. Beam and column joint. The horizontal part is the beam and vertical part is the column of this figure. The beam dimension, cross section of the beam is given on the right hand side. The beam depth, total depth is 20 inch, beam width is 10 inch. And this is the book problem, and the values are given there. There is a stirrup, 3/8 inch stirrup is there. This is number 3 bar, and the spacing of the stirrup is 6 inch center to center, and F primes is now start again. Here the beam is 10 by 20 inch, and the top rod is 1/4 inch dia main bar, and there are 2 bars, and it is the end of the beam, and then it is supported by this column, and this 2 number 10 bar is there. We are going to find out the development length of this number 10 bar. This is what is the value we require for giving this development length of this bar. The bar size is diameter of the bar is 1.25, that is number 10 bar, and the steel area of these two bar is 2.54. The bars are not painted, and the F prime C is 3 KSI, brick aggregate, and if there is a mistake in this printing one, if spacing is 3/18 size, 3/18 size stirrup is used, and the maximum spacing is 16 center. In this development length, we normally is required the maximum spacing, not the minimum spacings. That's why you have not mentioned the spacing near the column. Those are smaller spacing, but where the spacing is 16 center, that will come in effect. And these are the given values. We'll go for the calculation now. Next page. LD is the formula, as you have seen. This Fy is LD is equal to, using simplified. We have, first of all, we are trying to solve this problem with simplified formula. And as you know, the simplified formula is written here, as we have discussed earlier. And we have to put these values, different values, and the Fy is 60,000. We have to put it in, because F prime C is under root over. We will never use this Fy and F prime C in this equation in KSI. We have to put this value in PSI. That's why the Fy is 60,000, and it is a top bar. And for top bar, if it is more than 12-inch depth casting, then a factor of top bar is 1.3. That means at the top, the concrete is the water comes out at the top. While casting, the water comes out the top of the beam, and that's why that part of the concrete is not that strong, and therefore for the top bar we have to keep the development length 30% more. That's why we have given this 1.3 factor there. And for psi E, we have not used the painting here, painted bar here. That's why psi E remains painting is there. That's why that factor is 1. And as the lambda is, as the concrete is with of brick aggregate, concrete is made with brick aggregate. It is mentioned here somewhere that therefore the lambda is 0.85, and F prime C is 3000 given. When we have put these values, all these values, and after calculation we have found this 83.8, and that's the development length that provided. And now, as we have used the area more than the required one, the required value is 2.2, and for choosing the rod, we could not make this as 2.2. We have to choose bigger size of rod, and we have to take the advantage of that, and that is 2.2 divided by 2.54. 2.54 is the actual value, and 2.2 is the required value. That's why this the proportion of these two will give us a length of the development length of the bar less than the required one, that is 83.8. Is not, we will not use 83.8, but we will use 66, because we have advantage of the diameter, and the equation allows that if we use more area, we have to divide the development length by that area and multiply it by the area required. That's why here this comes as 16.6 inch. Now, with more accurate formula, first of all we have to find out center to center spacing of the bars. The width of the beam is 10, and there are two sides, that is, one is two sides of this beam. That's why we have put this 2. From 10 we have to deduct two sides, and the two-side clear cover is 1.5 plus the stirrup diameter is 0.38, and the half the bar diameter is 1.25 divided by 2. That all gives us 5. This is the value of C. So introduction spacing of the bar is half of this 5.5 is 2.5. Since cover to bar center is 1.5, side cover to bar center is 1.5 is actually clear cover, 0.38 is the diameter of the stirrup, and half the diameter of bar is 1.25 divided by 2, and that is equal to 2.73, and top cover is 2.5. Therefore, CB is equal to 2.5, because this out of these three requirements, the 2.5, 2.73 and 2.5 is the smallest one, and we have to put that CB, we have to take the value of CB as 2.5. Now in KTR equation, earlier we have discussed this equation and given this equation. We have to find out KTR. 40 is 40, ATR is area of transverse reinforcement. Area of transverse reinforcement. The stirrups are called as transverse reinforcement. These vertical rings are, they have two names. One is the transverse reinforcement, another is the stirrup, and here it is used as transverse reinforcement. 40 is 40, and transverse reinforcement area is 0.11, because we have used 3/8 inch dia bar, the area of which is 0.11 into multiplied by 2, and S is spacing the bar, as we have mentioned, this 5, and 2 is a number of bar in a section is 2. That's why it is 5 into 2, and the KTR is 0.88. Now CV plus KTR divided by dV. CV is there, and the 2.5, and KTR is 0.88, and dV diameter of the bar is 1.25, and that gives us a value of 2.70. And LD is, now we have to put 3 into 60,000 is the concrete steel strength, and 40 is the factor, 85 is the lambda factor, and remember 3000 is the concrete factor, and 1.3 is a top bar, and there is no epoxy, and the diameter of the bar, is 1.1, no painting, that's why this is 1, and diameter of the bar is 1.25, I'm sorry, and that divided by 2.5, and 40 into 8.5, these are the values required for formula, etc. And LD is equal to 63 inches. Required LD is equal to 63, and we require 2.2 steel area, and we have provided 2.54. That's the reverse proportion of this one will be coming up, and the area is 5.5. You can see if you use this formula,
required LD last time.
As we have used a little bit more area than the required one, that's why the development length will be inversely proportional to that one. That is, the required one is 2.2, and the provided one is 2.54. That's why we have to divide the calculated value of 63 inch into 2.2, and that will be divided by 2.54 will give us 54.56 is equal to 55 inch. We have to use a 55 inch length of this rod.
Yes.